Hi, Tiffany. Are we in the right place? I thought this is where the discovery talks are, right?
Yeah, I'm wondering if the room is not logged in. Do you know who's running the session?
This is a half plenary, which means it's a massive session.
But,
We were told there will be, it's a very big auditorium.
but who's running it?
Oh, it is run by Marcelle, Tim, and Aaron. Okay. I have sent a quick note to the three of them.
Are we an hour early?
No, it says 5:30. 3:30. Oh, you are right. Oh my God. I think we were 1 hour too early. You are right. Okay. I'm glad you were also there. We could resolve it. Okay. All right. I will join an hour later. Thank you.
All right, see you then.
Thanks. Yeah. Bye bye.
Testing. Testing.
Testing. Oh, testing. Does anything come out of it? Testing. Oh, we can do that for that one. Oh my gosh. Testing. Testing. You can't hear, right? Can you turn it up louder?
Well, maybe put in my,
Putty mic is this one, right?
yeah, but I don't know. Well, it has.
I think if you keep it as that one is like
Okay. Try again.
testing. Testing. Well, where is it? Where's the audio coming from actually? So it can't go up any louder. I think it can. Testing. Testing, testing. Testing. It doesn't go in. Testing. Testing. You hear it, right?
Yeah, it's coming out.
Testing. 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 Testing.
Mic test. Testing.
All right, I am assigning the captioner. Oops, sorry. Testing. Testing.
Oh, yeah, it's fine.
It was the first, I mean, Hey
How's it
man,
going?
how are you doing?
I'm doing well. What are you?
I'm good. Busy. It'll be a bit less busy after tomorrow morning, so that'll. And it's even that hard to play back in. So like with no reason that Jared put it. So we think we're connected to the we're connected to yeah, you just have to turn on the light. Okay. It's meant to be 20 plus 10, so 20 minutes before 10. Sorry, I may end up doing 20, 22, but if I'm at like 25, it's a problem. I need to stop. So it's meant to be 20 minutes from when I start. Yeah. So, yeah, you can give me the 5-minute warning at 15 minutes in from when I start. So were you guys waiting for me outside?
I thought we were in the next room and it was locked.
Oh, okay. No,
And they're
no,
in session.
we're in this room.
Oh.
Okay, very good. Very good. Yeah. Okay. Yeah, I said it was 20 plus 10. So give me the 5-minute warning, 15 minutes into the 1-minute warning. if you could do it if you want to, if you're worried about her ability to yell at me about going with that.
Yeah, I also am not sure like how long this will be, so.
Wait, let Aaron do it then.
20 minutes in line followed by 10 minutes.
Oh, like each.
Yeah.
20 minutes in line, so that 10 minutes mark.
So Aaron, so Marcel is the Zoom organizer for this, right?
Okay,
Is that how it works?
Yeah, and I'm supposed to be the in-person organizer, so
Yeah.
I guess she'll flash the cards.
Well, okay, just make sure that you're gonna flash the card?
Sure.
Yeah.
Okay.
We're gonna pick her eyes.
I mean, you should feel free to have a seat.
No, they did, but I only had a
Just so long as I know what you are,
Okay.
then I'll know what you are.
And are the other talks on here?
They're on, yep, the other talks are on here. The students, so do you know between talks will you guys like,
I'll
upload
switch
the
it.
next one?
You'll switch it.
Yeah.
This is the pointer down,
Oh. Thank
laser.
you.
So, and I'll hand this over to you.
Okay, that's really great. And then, so speakers, can we speak maskless or what's the policy there?
We should take off our masks once we're the only person at the podium and we're distant from everyone else, is my understanding.
And then with discussion, so they could be heard on Zoom, they will be.
Okay, so you'll help them.
Yeah, I'll help with pass.
We don't need to.
Okay, thank you.
And I'm assuming I get 20 minutes from when I start, not 20 minutes from 3:30.
Yeah, that's right. So unfortunately, so the other session just cleared out. And I don't know, should we wait a couple of minutes, you think? I think we can wait a couple of minutes.
Is it? I just want to make sure someone's logged into Zoom so that they can see if the people on Zoom are like, they cannot hear anything.
Okay.
If this is about you, if you're wanting to hear about muon colliders, this is almost testing, testing. Can people on Zoom hear me?
Yes, we can.
People on Zoom can hear me? Very good. Okay.
Is this microphone working?
Don't know if that
Yes.
works. Which students have one for questions, which they might be able to bring back to you for the intro. They can hear me through this, which is good.
I was just going to start the session. Could hear. Hello, is this microphone working for people on Zoom?
Yeah, both the microphones are working.
Yes.
Okay, so apologize, we're getting started a little bit late here, but we'll be started soon. There's still people walking in. So just so that everyone's clear, it seems like there's been a number of room changes, and this session is indeed a Cosmic Frontier plenary session. So if you're here to hear, if you want to hear about lepton colliders and stuff, you should be in the other room next door. But this is Cosmic Frontier.
Although I will mention lepton colliders briefly.
Okay, and my name is Aaron Cho. I'm one of the co-conveners for the Cosmic Frontier. And this is the first of our 2 plenary sessions. We have another one on Thursday evening, which will be more of a summary of the findings from the Cosmic Frontier study, and then a panel discussion of what various people in the community think is most interesting science to be done in this area. But today we're going to be doing something a little bit fun and different. We've asked 3 members of our community to compose some fan fiction of some exciting things that could develop with the experiments that are in progress or expected to come online in the next decade. And so we're just going to have a little bit of fun with it. And our first speaker for the day for this afternoon is Tracy Slotyer from MIT. He's going to tell us a little bit about dark matter. And the format is going to be, we're going to have 20 minutes of her giving a very interesting story of what might happen and think about the possibilities. And then we'll finish with 10 minutes for questions from the audience, and we'll alternate between people in the room and people remote to give everyone a chance to participate. So yeah, so welcome, Tracy. You have 20 minutes. Thank you.
Okay, great. Thanks very much, Aaron, for the introduction. I'm very honored to have been asked to give this talk and very happy to be here with all of you. I want to say thanks to everyone who gave feedback and made suggestions for this talk, and more broadly to everyone who wrote the white papers in the Cosmic Frontier and beyond that formed the foundations for the really exciting experimental program that I'm going to talk about. All right, so I probably do not need to sell to this audience that dark matter is an interesting problem. This is the word cloud for the SNOMAS letters of intent, with dark matter featured very prominently. what I would say is the nature of dark matter is an outstanding puzzle of fundamental physics. It's 84% of the matter in the universe, and we don't know what it is. We should try to figure that out. Dark matter is a challenge that crosses many frontiers, but in some sense, the cosmic frontier is its natural home. Our current knowledge of dark matter properties, our understanding of the problem, and our hopes for establishing its identity as the dark matter of the universe, rather than just a new particle in the spectrum, rely on cosmic frontier searches. So that is going to be my focus today.
Sorry to interrupt, but we are not able to see the screen on Zoom.
The slides should be shared on Zoom. Are you not able?
I can see them.
I can see them too.
Oh,
I
I'm
could see them as
sorry.
well.
I'm sorry.
Yes,
I'm sorry.
yeah, we can
Please
see
go ahead.
them.
Yeah, please go ahead. Yes, sorry, my mistake.
All right, I get another minute for that, right? Okay, so, all right. So what I want to talk about today is one possible path to discovery related to dark matter at the cosmic frontier. So the coming decade will be a really exciting time for searchers aiming to characterize dark matter across the cosmic frontier and more broadly. A non-exhaustive list of examples, biased towards what I'm going to talk about today, is that for the first time, axion searchers will have sensitivity to the QCD axion, not just in a narrow slice of parameter space, but across a vast mass range. Mature direct detection technologies will be able to probe orders of magnitude of new parameter space down into the neutrino fog, covering a range of highly motivated and parsimonious scenarios, by which I mean you don't need a lot of extra ingredients or knobs to turn. New technologies allowing detection of very low energy recoils of dark matter recoiling off nuclei or electrons will test entirely new physical regimes and new scenarios for how dark matter might be produced in the early universe. And photon and cosmic ray telescopes will be able to probe the simplest version of thermorelic dark matter up to masses comparable to the unitarity bound at the 100 TeV scale, as well as seeking signals in entirely new background-free channels. So what I'm going to do with this talk, as Aaron said, this is fun, this is fan fiction, maybe. Here we're going to explore one optimistic scenario for the discoveries that these advances in this experimental program could unlock over the next 10 to 15 years. Now, some caveats. There are a multitude of well-motivated possibilities for dark matter. We're going to talk about a very small number of them relative to the range of possibilities. I'm going to focus in my talk on probing dark matter through its possible non-gravitational interactions with visible particles. But even in the absence of such interactions, there are still powerful cosmic probes of the dark matter mass and spin and velocity and self-interactions and distributions throughout the universe, which I believe my colleague Risa Wexler will talk about a bit more in her talk. And that complements the search channels that I will discuss. Additionally, there's another somewhat arbitrary choice that I made. There are currently a number of interesting excesses and anomalies in indirect and direct detection. For the purposes of this talk, I am going to assume that all of these are telling us about places where we need to understand the backgrounds or systematics better, as opposed to new dark matter signals. One of them absolutely could be hiding a dark matter signal, but there's already quite a bit of literature about the paths forward if that is the case. So here we're going to do something different. So now we are entering hypothetical cosmos, where we have the cosmic frontier has a really great next 10 to 15 years. All right, so let's jump forward in time. It is late 2023. The SNOMES process is behind us. P5 has opined. We have a really exciting program of cosmic frontier experiments going forward. And in particular, in late 2023, early 2024, we get a couple of very interesting experimental results from two experiments in particular. So Sensei 100 gram is currently running. This is a new experiment looking for very low energy recoils from dark matter scattering on electrons. And now in late 23, early 24, Sensei finds a small excess in their lower spin above threshold. So it's a near threshold excess. Simultaneously, the GAPS experiment, which is a balloon experiment searching for low energy cosmic ray antideuterons, which are believed to be an essentially background-free channel for dark matter detection, has its first flight scheduled for 2023. They gather the data and they see one really clean event that looks like an antideuteron. So now that I've told you that, we're gonna have the larger version of this. So what would the community interpret from this? So the Sensei signal would be immediately clear, would look consistent with either roughly EV scale dark matter being absorbed on the detector or few MEV scale dark matter scattering on the electrons and depositing its kinetic energy in the detector. So the question would be, all right, how do we distinguish these possibilities and distinguish both of them from some kind of background? The GAPS result would just be an amazing step forward in that it would be the first detection of low energy antideuterons from any source. As I said, this is an effectively background-free channel. But as a dark matter signal, it doesn't quite point to the same parameter range as Sensei. Antideuterons are a couple of GeV. So this would suggest some kind of new source of antideuterons at some higher mass scale above a few GeV. All right, let's jump forward in time again to now sort of 2026 or so. And in the meantime, the theory community and all the members of these experimental teams and other experiments would be beavering away in the background. But then around 2026, we'd get another couple of very interesting results. So the LZ experiment, we saw the first results from that just a week ago. By 2025 and 2026, it'll be finishing its first run. So as LZ and its counterpart experiment Xenon and TON report full run results, in this universe, each of them detects a handful of events. Not enough to claim a 5 sigma detection, but their limits are weaker than you would have expected them to be at high dark matter masses. And simultaneously, on the indirect detection side, the AMS-02 experiment, which is on the International Space Station and measures cosmic rays, both reports its first antideuteron candidate and reports its spectrum of antiprotons, which is a spectrum of high energy antiprotons extending up above 500 GeV. So again, the question would be, all right, how do we interpret these things? This is very exciting. This is the kind of signal we've been waiting for a long time. But what does it mean? Well, for the antiprotons, the community there's been an active push in the community over the last few years to get better models for how cosmic rays are produced and propagate through the galaxy, including accelerator searches that can try to better nail down the relevant cross sections. And those studies by now in 2026 or so have significantly reduced the theory uncertainties for AMS-02, meaning that now people look at the spectrum and start to say, that really is more high energy antiprotons than we thought should be there. But all right, so that's maybe intriguing. The detection of events in LZ and Xenon and TON would of course trigger further intensive study of possible backgrounds in Xenon experiments. If they see just a few events, they'll be getting very close to what we call the neutrino fog, when neutrinos actually start to become an important background for these large Xenon experiments. So there would be an intensive study of all possible backgrounds that could be giving rise to these sources. Around the same time, in 2027 or so, that Sensei XS would have been interesting, but still maybe a background at this stage. But in 2027, the successor experiment to Sensei, DAMIC-M, which would have a mass 10 times that of Sensei, and again would be looking for low threshold recoils, confirms a signal comparable to Sensei, but now with much higher statistics. It's still in the lowest energy bin, still above the threshold. It's still somewhere you have to worry about backgrounds. But at this point, both experiments will be trying to study modulation effects in their data sets over time. So there would then again be an intensive effort to study the backgrounds and threshold effects in experiments of this type. We could look at results from other frontiers at this point as we started to take this XS more seriously. Accelerator experiments, especially those with electron beams, could test the coupling of dark matter to electrons and thus the possibility that dark matter is scattering off electrons in these experiments. Null results, of course, a positive detection in those experiments would take you off on a whole different path. But in this universe, they get null results, and that constrains a significant amount of possibilities for this Sensei and DAMIC signal. The modulation studies in these experiments could look for both annual modulation caused by the Earth's motion around the sun, or even modulation on shorter timescales like the daily modulation from the rotation of the Earth. And as we started to see modulation signals consistent with expectations from dark matter, that would increase our probability that we were actually looking at something like dark matter. On the indirect detection front, with these new results from AMS-02, and with multi-wavelength data from other experiments, the community would be working to develop new models for high energy galactic gamma ray emission, because at this stage in the timeline, we could have large ground-based gamma ray telescopes, CTA and SWGO, under construction and getting ready to take data. So you thought I was going to put an indirect detection thing on the board now with that, but before the indirect detection, before the gamma ray experiments can report results, a new contender enters the game. When DM radio meter cubed detects a signal that looks consistent with a light axion with a QCD type coupling. So DM radio meter cubed is a new experiment seeking to probe the QCD axion across many orders of magnitude and mass. This is a heroic experiment. ADM-XEFR is the counterpart that will probe the QCD axion at higher mass, and they're both ready to go. So in this universe, DM radio gets lucky, and it turns out that there appears to be something like an 0.1 micro-eV axion-like particle in our cosmos. So again, so this would immediately raise the question, all right, it looks kind of like a QCD axion. Is this actually a QCD axion? If it is a QCD axion, this detection would immediately suggest new physics up at the 10 to the 14 GeV scale. So we would have, this would be one of our highest energy probes of new physics, suggesting maybe we should be looking for new physics up there. How would we do that? Well, one method is through cosmology. Such a QCD axion, to get the right amount of dark matter in the present day universe, would have to be created prior to inflation. So this observation, under the assumption that what you're seeing is actually a QCD axion, would immediately set an upper bound on the scale of inflation. And now we have the now we have indirect detection coming in. So GAPS, that is a balloon experiment. It can fly multiple times. It has 3 flights scheduled at the moment. I have been a little cruel to GAPS here, since I have assumed that they would not get a ton more flights as soon as they saw the first anti-deuteron. But on their current scale, and I've assumed also that their second flight didn't see any anti-deuterons. But the third GAPS flight flies, reports more anti-deuterons, and gives us signal, okay, maybe this wasn't just a fluke. Maybe there really is some exotic source of low energy anti-deuterons which needs to be explained. And at the same time, CTA, which is the big next generation gamma ray telescope that the field has been waiting for many years, takes data, looks at the galactic center, compares what they see in the galactic center to these background models built out of cosmic ray data from a range of other experiments and observations of the galaxies at other wavelengths, and says, that's funny. There's quite a lot more TeV scale gamma ray emission coming from the galactic center region than we might have expected. And so again, what would we do with this? Well, theorists would of course be like, all right, we've got anti-deuterons, we've got new physics above the GeV scale, we've got more high energy antiprotons than we expected, we've got more TeV scale gamma rays than we expected, let's fit them all together and see what it implies. And the community would find that there is a consistent explanation for these excesses in terms of multi-TeV dark matter annihilating primarily to quarks. The presence of the anti-deuterons tells you that you need to be making a lot of quarks in this decay. But a funny feature of this would be that when people infer what the cross-section needs to be to get this signal, it would be somewhat larger than the thermal relic cross-section, which we like to use as a benchmark. So this would imply either some kind of if this was dark matter, this would imply either some kind of non-thermal history in the early universe or some kind of late time enhancement to the annihilation, which at present would tell us quite a lot about the properties of the dark matter. All right, now we're in 2030. So in 2030 is the timescale on which the next to next successor to Sensei would be able to report results. This is Oscura. So this is again scaled up by a factor of 10 version of DAMIC-M. So with that kind of size, Oscurus could start getting enough statistics to really try to measure the recoil spectrum at scales above NeV. Simultaneously, by that point, Super CDMS, which is a long-running experiment but has been really pushing to get their energy thresholds down to lower levels, would actually have a comparable energy threshold level to these dedicated Sensei and DAMIC and Oscura experiments, and could independently confirm this detection through a completely independent method. So now the community, I think a large chunk of the community would be very focused on, all right, what is this EV signal? It appears to be real. It's confirmed in 2 types of experiments. What could it be? Just as the electron beam experiments would still be giving us constraints on how dark matter couples to electrons, at this point, we could also have MEV band gamma ray telescopes in orbit, setting stringent constraints on how dark matter annihilates or decays producing gamma rays. And the non-detection of gamma ray signals from dark matter could also rule out some of the parameter space for MEV scale dark matter producing the Sensei excess. If the true explanation was the EV scale dark matter was getting absorbed in this picture, that's potentially testable by cosmological searches for EV scale light relics. On the axion side of things, as soon as dark matter radio detects an axion signal, it can be used as a dark matter telescope. By observing the strength of the signal over time, DM radio could map the presence or absence of axion clumps in the dark matter halo, which is a wonderful input to axion model builders trying to understand what kind of axion or axion-like particle we could be looking at. It could also enable possible tests. You might be starting to suspect at this point, maybe this axion is not 100% of the dark matter. Would potentially allow us to test what fraction of the dark matter was made of axions by comparison to cosmic probes of dark matter structure. Over on the direct detection side of things, I guess I forgot to be explicit about this, but blue here means low threshold direct detection, red means higher threshold, large volume direct detection, green means axion searches, and yellow means indirect detection. So over on the direct detection side of things, if we can wait till the early 2030s, that's when we would get a possible counterpart detection in argon of the previous detections in xenon. So here again, now we would see a signal that had been detected through multiple methods, through multiple target materials. And that would allow us to start asking questions about, all right, how does this dark matter candidate couple to the standard model? Combined fits to xenon and argon and to the indirect detection searches, if you want to say, all right, let's hypothesize that these signals in direct detection and indirect detection are the same thing, could start to place stringent constraints on the operators and couplings that connect the dark matter to the standard model. Also in the early 2030s would be a great time for the whole field under this scenario. We would have 2 large ground-based gamma ray experiments observing the inner galaxy. SWGO, the Southern Wide Field Gamma Ray Observatory, would look for gamma rays at the TeV to 100 TeV and higher scale, and it has a large field of view, so it can see large fractions of the galaxy at once. And with that capability, it would be able to look at the galactic center as an extended source and map out the distribution of the emission. So SWGO turns on and reports not just that they see high energy gamma rays from the galactic center, but that the morphology looks consistent with annihilation from a dark matter halo with a flattened core. And on the other hand, CTA, which will have a really good energy resolution, could detect a faint gamma ray line, which would give us a handle on the mass of whatever was producing this. In this picture, it's at 7.5 TeV. So this would suggest a mass scale of 7.5 TeV. Combining this data would allow us to break the degeneracy between the cross-section and the halo profile. We can actually measure the halo profile once we have enough gamma rays. The improved background modeling the community had been working on all along, and the multi-messenger spectrum of cosmic rays and gamma rays in this signal would really allow you to start nailing down how is this dark matter candidate annihilating? What are its subdominant branching ratios? We know it makes a lot of quarks. What other kinds of standard model particles does it couple to? On the axion front, the early 2030s is also when we could get a confirmation through a different method of the DM radio detection with the SRF meter cubed experiment, which is going to follow up in the same mass range. And once you have multiple experiments with detections in the axion space, you can actually try to measure the 3D structure of the halo because the different experiments can see different phases for the axion signal, as well as, of course, just being a great test of systematics in your detection. Over on the light dark matter side, the issue with all of these previous searches was that the signal was right at their threshold, which makes it hard to tell the difference between different spectra and different possibilities. But research and development in these low threshold direct detection experiments could enable much lower thresholds in the not very distant future. So in this scenario, in the early 2030s, Tesseract achieves energy resolution of an energy threshold of 0.01 eV, and thus is able to measure the low energy spectrum. And the low energy spectrum is very sensitive to the velocity dependence of the scattering. This would allow you to immediately rule out the absorption hypothesis and point to dark matter scattering off electrons through a very light mediator. And at this point, the theory community will be like, we know what this is. The signal, we know there's a light mediator in the problem. We can calculate how the dark matter would be produced in the early universe from the interactions of the light mediator with the standard model through the Friesen mechanism. And they'll say, this signal is consistent with the subdominant Friesen component. Moving back to direct detection with high energy thresholds, but unprecedented sensitivity to cross sections. This is about when we would get the next generation, third generation xenon experiments, which again would now no longer be measuring just a small handful of events, but could measure the recoil spectrum more precisely, measure the distribution of the dark matter velocities for the heavy dark matter component. One thing that these direct detection experiments won't be able to do very well is measure the mass if it's very heavy, like much heavier than all the targets. But that's fine. We've got the indirect detection side of things to tell us what the mass scale is. And on the axion side, I asked that question earlier, like, is this actually a QCD axion that we're looking at? Well, that question would always be pretty ambiguous until we can measure couplings other than the coupling between axions and photons. But there are experiments in the portfolio that could do that as well in the not too distant future. So the CASPER experiment has plans to detect a range of possible different couplings between axions and standard model particles. And in particular, in this scenario, it would detect the defining coupling of the QCD axion, which determines what kind of electric dipole moment it gives to the neutron. So this would serve as a consistency check on the QCD axion explanation for this excess, and combining the measurements of axion photon coupling and this axion EDM coupling would really constrain what kind of axion models that you're looking at. And that could point to new expanded Higgs sectors or new quarks that could potentially be searched for at a next generation collider. Okay, so we're coming to the end of our timeline, and I am coming to the end of my time. So I'll just wrap up with a few kind of speculative things at the end of the timeline. By of course, this is all speculative and all optimistic. This is even more speculative. So, so by this period, we could have multiple really sensitive MEV band experiments in space. We could also potentially have a successor to the Fermi Gamma Ray Space Telescope, the Advanced Particle Astrophysics Telescope, or APT. So in this scenario, APT finds something pretty unexpected that correlated with the high energy gamma ray emission that SWGO and CTA are seeing. It sees a series, a forest of gamma ray lines at tens of GeV, and sensitive MEV band experiments with really high energy resolution find even lower energy counterparts. If something like this happened, what this could suggest is additional structure in the heavy dark matter candidate, like excited states or the presence of bound states. We could do dark matter spectroscopy. This is my dream scenario, but it's okay. By using these gamma ray experiments to look at different targets at dwarf galaxies and at clusters, we could also measure the velocity dependence of the signal, which would allow us to test for new dark forces and reveal the consistency or lack thereof of this signal with a thermal freeze-out scenario. And maybe at the very end of the timeline, this is my colleague in CF7's favorite scenario, we will have at that point detectors for really, really high energy gamma rays and neutrinos such as GCOS and POEMA, which have greater effective area than by an order of magnitude than the combined effective area of all the experiments before, sorry, I guess I mean exposure, not effective area, than the combined exposure of all experiments before them. So at the end of this timeline, one of them sees a 10 to the 12 GeV photon coming from the galactic center. So what is that? It could be included in new high scale physics. Could it be connected to this axion that we've just said could be connected to a 10 to the 14 GeV, new scale? Who knows? All right, so, okay, this is of course dark matter fan fiction. This is, but I hope this has illustrated you to some degree the breadth and reach of the experimental program that is being proposed in the cosmic frontier. If we did have something like this, where we would stand, I don't know if I can move that at the, is there any way to move that bar so that it moves away from my conclusions? Like to the bottom would be fine. So what we would be looking at if this was the situation in 2035 would be, we would have evidence for a 7.5 TeV heavy dark matter candidate that looks at least broadly consistent with a thermal relic, but maybe with enhanced annihilations at late times. We would have an MEV dark sector possibly populated by a freeze-in with a much lighter mediator, and we would have 100 nano EV QCD axion. Now, then you would ask, okay, like, is this really 3 dark sectors or is this 1 dark sector? Do these particles interact with each other? Are they connected to each other by some new unifying principle? What is the associated spectrum of particles that are not the dark matter? We know there has to be some mediator to the standard model, but what else is going on here? So this would be a bonanza for theorists, but it would also be a bonanza for the experimental program. There would be many new opportunities to follow this up with future experiments. So we would have strong evidence for a new high scale in physics, which we could potentially try to look at with cosmological searches, with ultra high energy cosmic rays, gamma rays, and neutrinos, with gravitational waves, and even with searches for ultra heavy dark matter on the chance that there's another stable component in the spectrum. We know we would have evidence of a new MEV dark sector. So we could search for light particles associated with that. Cosmology sets some powerful constraints on new physics at the MEV scale and lower, since that's the scale of Big Bang nucleosynthesis. The axion experiments are trying to seek to, are looking to expand into more general searches for wave-like scalar and vector dark matter. They could have sensitivity to other ultralight stable states in this sector. Beyond the neutrino fog, directional detection and paleo detectors could offer options to map out the dark matter halo, both in the present day and in the past history of the Earth. And once we had actual confirmed detections of antideuterons, future cosmic ray experiments could use antideuterons and antihelium as a new cosmic probe. I haven't talked much about neutrino counterparts here, but KM3net or successors could potentially have sensitivity to this 7.5 TeV dark matter candidate and related particles. And if something like this 7.5 TeV dark matter candidate did exist, coupling directly to the standard model, it would actually be a great target for the muon collider that our colleagues in the other room are talking about. I found a forecast paper from last year that said if you had a 20 TeV center of mass muon collider, you would find this thing. So, okay, that's one path or set of paths. There are a ton of paths that I could have taken and did not today. But one thing that I want to stress to you is the program I have outlined is actually very versatile. If I had changed my parameters a bit, then in most cases, these signals would still have been found, just maybe by different experiments. For example, if I had made my QCD axion a couple of orders of magnitude heavier, it would still be found by ADMX EFR or even heavier scales by other experiments. And it could also have striking cosmological signatures that could show up in cosmic probes. If I had said, all right, I don't like MEV scale dark sectors, I want a GeV scale dark sector scattering on nucleons, then the first detection would likely be by super CDMS, not by Sensate, but it would still be found. If I had made my 7.5 TeV thermal WIMP, and it is actually a real, like a real thermal WIMP candidate, I know what the model is. If it was an order of magnitude heavier, if it was a 75 TeV thermal WIMP, the Southern Wide Field Gamma Ray Observatory will still have sensitivity to that candidate. Although again, the exact order of detections might change around. And there are many more examples. So this is one thing that I'd like you to take away from this. The proposed program here is really versatile and would cover a great deal of ground. So some general lessons that I got from doing this exercise. One is that doing this exercise made me more excited about the Cosmic Frontier program. This decade will really see great advances in sensitivity across an enormous range of models and detection channels. I've tried to talk about two forms of complementarity here, both of which I think are valuable. One is that a broad multi-scale experimental program allows us to test a lot of different scenarios and maximize our possibility for discovery. But the other one is that in the event of a detection, such a program also enables us to cross-check both with complementary detections and with null results, what's going on, and really triangulate the properties of the dark matter. I hope I've conveyed this, but if this was happening, it would be really confusing in the moment. To understand what these sensitive experiments are actually telling us, support for theory and the study of systematics backgrounds and calibration would be absolutely essential. And with regard to the specific scenario classes, the one I picked, thermorelic dark matter remains well motivated. The example I used is actually a very minimal classic WIMP model. It's fine. Multi-wavelength and multi-messenger indirect signals, especially for heavy dark matter, are completely natural and would be very powerful in narrowing down its properties. Low threshold direct detection has really unique abilities and a ton of avenues to follow up a first detection. And axion searches are really, for the first time, well positioned to probe the QCD axion and beyond from multiple directions and across a wide range of masses. And finally, if we got any of these detections, any discovery in Cosmic Frontier search channels, it would potentially open up the opportunity to learn about the composition and distribution and velocity of dark matter throughout our galaxy and beyond with unprecedented precision. And that in turn could teach us about the history of our cosmos. And I'll stop there.
Thank you, Tracy. We did go a little bit
Sorry,
over
I
time,
could not.
but,
Yeah, I
it was
didn't
going
see
so well, I didn't want to interrupt. So maybe we have time for just a couple of questions, and I'm sure Tracy would be happy to talk offline as well.
I'm very happy to talk.
Yeah, are there any questions from this audience in person, first of all? Well, how about there seems to be at least something in the chat. No?
There's a question there.
Yeah, please say your name for the remote audience.
All right, Phil Harris, MIT. So presumably, if we had all these discoveries, we would probably want to inject more money and more experiments. What would, in this fan fiction scenario, what would you extend the program on?
There are a lot of, I mean, well, I think at this point, I mean, you're right, like maybe we would need to move the next snowmass forward a bit, but I mean, this would be a question for the next snowmass, right? It's, you know, you could, yeah, so I mean, as I've said, this is kind of a maximalist version of the program. More realistic scenario might be that, you know, if we inject money into one of these directions and maybe we see one of these things. But So on the, I mean, on the axion detection experiments, like once you know where to look, once you no longer have to scan over masses, then there's the possibility to build more experiments, be able to triangulate the halo, be able to go deeper. I will also say, I'm a theorist, so asking like what would be your dream scenario next for experimentalists, like I may not be the best person to answer it. There are probably better people to answer it in this room, but certainly on the axion experiments, once you know where you're looking, you can drill deep on that point. On the low mass direct detection stuff, again, if you knew that your target was really like, all right, we've got an EV scale thing, we just want to really measure its spectrum accurately, then that would be a direction to go there. I mean, it might maybe I sort of had my list of lots of ways to move forward. I mean, maybe this would stimulate us to say, right, we need to build a Buon collider and see what this 7.5 TeV thing is actually doing. I mean, that could be a direction for the field. I don't really want to forecast what that future SNOMAS would say, but I guess that, I guess I would just say that like there would be tons of exciting opportunities, and the difficult question would just be like, right, which of these opportunities do we follow up first? What is the most like efficient use of the resources that we have to try to figure out what's going on? But there would be a lot to do.
Okay, great. One more question from Pierre.
Thank you. That's a very nice presentation. And should we so lucky to find that much structure?
I'll be happy if we get one of the circles
Yeah.
on this
So
figure.
that's where my question was going. We've been looking for this for a number of years. 15 years ago, I could smell it. It was about to be the WIM paradigm and all of that. So what happens? Where do you go if none of these things show up?
Yeah, so I mean, like I said at the start, I do think that we are in a new era for at least some of these searches. Like, I think that the Axion searches really do have a good case that they're going to be able to probe the most well-motivated range of their parameter space comprehensively in a way that hasn't been done before. I think for the I think for the high energy gamma ray telescopes, they again could potentially push in a range where they really are testing some of the simplest scenarios over an enormously comprehensive range. But yeah, so suppose we do all this, we do this whole program, we don't see anything. All right, well, I think that a later talk in this session will offer some alternative answers to this problem, but to this question. But we could. I mean, I think I might lean at that point towards looking more closely at the cosmic probes and the cosmological probes of dark matter that my colleague Risa Wexler is going to talk about in a couple of talks. But again, I don't want to try to I think that at the moment we're at a point where there is potential for enormous improvements in sensitivity. If we don't see anything in 10 years, I think that is a question the next SNOMAS will have to think about very seriously. But I hope we see something.
Okay, I think we need to move on and maybe just one quick talk while Kyle sets up. Okay. So is it Annika, Peter?
Hey, yeah. Just to say that I don't want to steal Risa's thunder, but we do know dark matter interacts gravitationally, so I have a lot of hope. But also, you all should stay in the room and attend Risa's talk.
Okay, yeah, and our second speaker, sorry, I think we need to move on. And again, Tracy's happy to answer more questions offline. Our next speaker is Kyle Dawson from the University of Utah, and he's going to tell us a similarly exciting story about cosmic acceleration. And
okay, first,
okay,
I guess this mic is working, great. Okay, yes, great. So thank you everyone for coming here today. Also, I don't have a thank you here because there were so many people, I can't list them, but if you want to say briefly speaking, it's everyone in the CF4, the CF5, the CF6, and the CF7 groups, plus there's actually some information from CF3 as well. So thank you to everybody for helping with this. So I'm going to talk about cosmic surveys, cosmic observations. I'm going to try to paint a message that there's different regimes of discovery space. And for each regime, there are very well-defined, physically motivated measurement goals. So thresholds for a measurement that can set the design for an experiment. And they're going to be framed in 3 big topics: dark energy, inflation, and new physics from early universe messengers. The techniques span wavelengths or approaches. I'm going to talk about optical infrared spectroscopy, imaging, and the cosmic microwave background as the techniques to make these measurements. There's also gravitational wave observatories as well. The observables, of course, relate to the type of technique of the observatory. It's baryonic matter, dark matter, and gravitational waves. The scales we're talking about, again, we have observables across scales from galaxy clusters to the horizon scale. And in terms of epochs of cosmic history, the observables and the physics span from today's epoch back to the inflationary epoch. Okay? And the discovery potential is, some of it is rooted in very well-vetted, well-prescribed techniques. In addition, there are many, many new techniques in development that are guaranteed to result in some surprises. We don't know what yet. Okay, this will all be enabled by very high precision measurements across multiple probes. Will also allow for consistency and tests for new physics. So, saying everything I just said now in graphical form, here is that image of scale, technique, and time coverage, epochs in cosmic history, okay? So on the y-axis is scale, okay? From the smallest scales to the largest horizon scales. On the x-axis is time, redshift 0 today, back to the early universe. Here is different snapshots of our observables, ranging from large scale structure to imaging to intensity mapping to the cosmic microwave background. And within this parameter space, you see 6 different cosmological, questions about fundamental physics. I'm not going to cover astroprobes of dark matter. Risa will cover that. But what I'll do for each of these regimes, I will present what is the target measurement that's well motivated, that will set a design for a future facility or a current facility, and then what surprises can come out of it in addition. Okay. So let's start. The current stage 4 experiments, that's LSST and DESI, they're really optimized to explore the universe in this regime. Fairly low redshift, that's like 0 to 1.5, and fairly large scales. The design is set by the Dark Energy Task Force Figure of Merit. And the goal there, going back almost 20 years, is to go from discovery of dark energy to very high precision measurements. The techniques are expansion of history, growth of structure. And what these measurements reveal in stage 4 are questions about the equation state of dark energy and the fundamental properties of dark energy. We can reveal that maybe it's a vacuum energy, it could be an entirely new field, or it could require physics beyond general relativity. These are all possible scenarios. Beyond just measuring the redshift distance relationship or measuring growth of structure, the primary drivers, there's additional potentials for discovery. We're already starting to see tensions in this regard. It's often presented as the H0 tension, the Hubble constant tension. But in truth, the physics, if it is not on H0, the physics is on the early universe, expansion history, particle interactions, and anything else that sets the drag scale. Okay. So here you see that relationship between the drag scale and H0 and different probes, and you get different relationships between that drag scale, depending if you calibrate it locally with supernova and Cepheids, or with the CMB and standard models of physics. If it turns out that this tension is real and we get 2 different results, what that really requires is a modification to our model that gave us this R sub D measurement from the early universe observations. That would require something like neutrino couplings, a new particle or field, some alternate model for dark energy, some other physics that modifies the drag epoch, or the drag scale. And what we want in stage 4 are some probes that will naturally produce this, like strong lensing time delays, and also there's potential in things like neutron-neutron star binary mergers from gravitational waves. So the goal here would be to over-constrain those direct H0 measures to the percent level. Okay. So the next experiment is CMB stage 4. CMB stage 4 is recommended at a very high priority in the last P5 process. The primary science drivers are going to be inflation, specifically primordial gravitational waves. It also covers this regime here, which I'll talk about later. Okay. So the primary science driver that sets the design for the small aperture telescopes, the deep drilling fields, is to determine the tensor to scalar ratio at a threshold of R equals 0.001. And what this will tell us is what is the fundamental energy scale of inflation. And there's at least three clear scenarios given our current sensitivities. We could see a super Planckian mass scale at the highest allowed values of the tensor to scalar ratio. We can see the simplest models inflation at the threshold of the measurement. Or if the tensor to scalar ratio is less than this, that implies a model of a small field inflation. Beyond CMB stage 4, there is potential to explore the spectrum of gravitational waves. This is possible through gravitational wave observatories and pulsars. What you see here is the CMB stage 4 limit here at frequencies of like 10⁻18 to 10⁻16 hertz. Spanning much higher frequencies are those gravitational wave observatories. And what they can allow is other tests of inflation beyond the standard slow row model, other alternatives. Okay. Now, while CMB stage 4 was recommended at high priority in P5 in 2013, the next stage beyond LSST and DESI would be a large stage 5 spectroscopic survey that's been discussed in great detail in CF 3, 4, 5, and 6. And while I draw a very large box here, I'll show on the next slide, it actually couples to all the other observables as well. But the design would be to cover scales out to a redshift about 4 and down to scales actually including astrophysical probes of dark matter. But what I'll talk about here is the small scales that are still cosmological, which is 1 megaparsec. Okay. So when we look at the stage 5 spectroscopic survey, what is it, first of all? It's a massively multiplex spectrograph on a large aperture telescope. It would be designed to allow more than an order of magnitude improvement on survey speed over the current facilities, more than an order of magnitude increase on sample size of the highest redshift galaxies, Z greater than 2, and samples less at lower redshift that could achieve near sample variance limit on cosmological scales. Important to note that DESI is operating, it's doing great, it's ahead of schedule, it will exceed what those stage 4 requirements are, and it can also serve as a roadmap to the stage 5 facility. It can help characterize the samples, it can make the very high precision measurements of the distance redshift relationship at high redshift, and also help develop new techniques for structure growth measurements. And as I mentioned before, this spectroscopic survey does not happen in isolation. All the measurements I'm going to show from here on out really require complementary probes from the imaging and CMB facilities. The full constraints are only possible with the full suite of measurements. Okay. So the primary science driver would probably set the survey design for a stage 5 spectroscopic facility is primordial non-Gaussianity. That's up in this corner right here. This is another feature of inflation that complements the primordial gravitational waves for CMB stage 4. When we talk about this, we talk about non-Gaussianity. We often characterize it as the different qualities of non-Gaussianity. There's local, orthogonal, equilateral. The most common that's used to set our goals is the local version. And that allows us to determine whether or not inflation is a single field or multi-field, depending on the value of this non-Gaussianity parameter. This is the observable in 2D space in the power spectrum. It actually has additional sensitivity in the bispectrum. The bispectrum and all these measurements, whether it's the orthogonal, the equilateral, they all allow us to probe for no Gaussianity and check the dynamics of inflation. We'll get a different measurements of excited states in the inflationary field, particle interactions, et cetera, in that early time. Those same data that will be used or could be used to make that FNL measurement, they will also produce a large number density clustering sample at high redshift in regimes where we don't yet have good sensitivity with BAO measurements. We can make those BAO measurements at very high precision, extend the redshift distance relationship past redshift 2. And with those measurements, we can test for early dark energy. We can test for non-zero global curvature and any tensions in the concordance model by making measurements at comparable precision to what we're doing at low redshift, and now extending that out 10, 12 billion years in the past. Okay. Next area is low redshift, very, very high number density, probing to small scales and saturating the cosmological content. So this is a recommendation that came out of the Decadal survey, is to measure the growth of structure. It's characterized as the sigma 8 parameter to 0.2% precision. This not only gives us another view into the expansion history of the cosmos, it also allows us to test for modifications of general relativity, look for new fields of interactions through comparison of the low redshift cosmos to the high redshift, and also look for new properties of dark matter. Okay. The same time, again, those same data, because they are getting such high precision measurements of the power spectrum over all scales, there's many, many modes there. It will allow a 1 to 2 order of magnitude improvement in search for departure for scale invariance from the inflationary field. So more inflationary physics now, you can test for that at low redshift, at redshift 0. There's lots of different physics that can produce departures from scale invariance. There's everything from axions to periodic corrections to inflationary potential. Okay, so last, I'm wrapping up here. I'm combining these last two areas just for sake of time. They're both related to neutrinos and other light particles. The scales, again, subtend from about redshift 1 up to the CMB. And they also scale back to the physics that was discussed in the SNOMAS 2013 process. So one of the primary drivers in 2013 was to be able to measure the sum of the neutrino masses to a precision of 15 millielectron volts. That is well within the reach of these future facilities. What that will allow us to do is not only determine the absolute neutrino mass at that level of precision, but also you can differentiate the normal hierarchy from the inverted hierarchy at up to 3 sigma. If you get tensions or differences from terrestrial measurements in the neutrino mass, that also is indicating that the physics that we're picking up in our cosmology, our cosmological surveys, is different from what's in the terrestrial surveys. So there's some other feature, some other particle that's contributing to mimic what we'd call the neutrino mass. So finally, looking out back to the earliest times in the inflationary history, like right after the end of the inflationary epoch, we have a parameter called N effective. It tells you what is the thermal history of the cosmos and the precision in which you can measure N effective within that limit of thermal physics. You can scale back to times at the end of the inflationary period. So you really can get the full particle contents of the universe since inflation. Anything beyond the standard model, if you have just the standard model of particles, you get a very high precision estimate. The N effective should be about 3.04. Okay? So you can get a very strong null test. If you can make this measurement at 0.027, you can look for the axion-like particles and different properties of the dark sector. So there's a really wide parameter space here. Even though there's a lot of different physical questions here, my take-home message is each region in this space has a lot of cosmological signal. Each region has a very well-defined goal for cosmological measurement that's tied to fundamental physics, where we can have an answer plus or minus on some fundamental property. Some of it's inflationary questions, some of it's dark energy, some of it's beyond standard model physics. Okay. The CF4 to CF7, they provide the roadmap to these discoveries. I presented the stage 4 dark energy experiments. I presented CMB stage 4, a stage 5 spectroscopic survey. In addition, there's proposals or advocacy to develop the technology for future line intensity mapping surveys. They would allow you to push to even higher redshift where there's more information content from the stage 5 spectroscopic survey. There's also advocacy for the gravitational wave observatories. So with that, I'll wrap up and take questions.
All right, thank you very much, Kyle. And maybe we'll start. Are there any questions from the online audience right now? Not yet. Okay. So any questions from the room? People are still thinking.
Yes, so I'm Tracy Slatcher from MIT. Can you talk a bit about the kinds of inflationary scenarios that would be probed by this, and for the ones that you can't reach, like what are there next steps beyond this SNOMAS?
Okay, so let's see. So let's look at this figure right here. So right here, you can actually really probe fundamental inflationary scenarios on basically what is the energy scale of the inflationary field. So that's a very specific observable. If it is within the measurable range that I provided you, you will learn that. If it's below that, you'll learn that you're in more of a small field regime. So you'll definitely will learn that about it. But then you start running into fundamental limits in the measurement. The CMB stage 4 community can talk about more about that. But I think if you don't measure, if you measure R to be significantly less than 0.001 within observational confidence, I don't know. I think you then start asking, what are the other features of inflation? What is the non-Gaussianity features?
Yep, makes sense. Thanks. Yes, well,
I think if you also measure R to be greater than that, you still ask those same questions. What are the features that you probe through the non-Gaussianity?
Great, thanks.
Right. Anything from the online audience? No. Last call for questions. And if not, maybe we can, Risa can start getting. Oh, okay. One more.
Yeah, I guess like as a theorist, I'm curious as to the degree, do we need new theoretical techniques to understand these? I know this is an experimental frontier talk. I'm just curious as to, are these places where there are, major new directions for theory as well?
Yeah, so in the talk I gave for the SNOMAS colloquium, I get into that.
Great.
And so there definitely are questions in all these regimes for theory. The thing I personally find the most, I'm the most interested in having theoretical development is this regime right here. So here we can measure, we have an infinite number of galaxies to measure. We can measure them very easily. We can measure things to basically the cosmic variance limit over all cosmological regimes. The question is, can we theoretically use weak lensing, 3-point systems, other techniques to constrain the astrophysical nuisance parameters? Or another way of saying it is, how can you use all the different observations to disentangle the astrophysics from the fundamental physics? And that is a big challenge because the current EFT models have enough flexibility at these small scales to soak up that cosmological information. So we need people to look at these EFT models and really nail down those nuisance terms.
It's a very different kind of backgrounds and calibration problem than the one in the probes that I talked about. But yeah, it's again that we need to be able to separate the fundamental physics from the astrophysics. Thanks very much.
Yeah, so like baryonic physics, nonlinear clustering, things like that.
Thank you.
Okay, great. So yeah, thank you very much again, Kyle. And our next speaker is Risa Wexler from Stanford and SLAC, who's going to tell us about how to probe for dark matter using cosmic probes. And I'll let her explain what that means.
Okay. Okay, delighted to be here. Thanks for the invitation to give this talk. Let me just say at the outset that just like Tracy said, preparing this talk actually made me even more excited than I already was about the next decade. And so I'm gonna kind of follow on the previous two talks and primarily talk about pathways to discovering dark matter, but I'm gonna base that on the connections to cosmic probes, many of which use the same facilities that you heard about from Kyle. So how do I, there we go. First, let me just say, first of all, I'm not a particle physicist. I'm a cosmologist who mostly works on cosmological structure formation. So I learned a lot in the last couple of weeks preparing this talk, especially from some of these people, but also from all of the people who contributed to CF3 white papers and to the CF1, 2, and 3 reports that I have been heavily leaning on. So thank you to everyone. So I thought I would just start by setting the stage of, by my count, we have roughly 90 orders of magnitude possible for the dark matter mass. And in this version of a plot that you've probably seen other versions of before, I wanted to highlight, so first of all, we have CF1, which is particle dark matter, roughly from, an EV up to, a few hundred TeV. We have wave-like dark matter, which is in CF2, which goes from 10 to the minus 21 or 22 EV all the way up to an EV. And then we have cosmic probes of dark matter. And the great thing about cosmic probes is you can go all the way from the scale of a planet to the scale of a whole universe. And that means that they can essentially, through different mechanisms, probe almost this entire range of dark matter masses. And in fact, not only do they probe this entire range, I think they also give the most useful bounds on this range. So at the low mass end, you can't go lower than this because it would suppress cosmological structure formation that we've already measured. And at the high mass end, you can't go higher than this because it's ruled out by things like microlensing. There are actually a number of other probes at the high mass end. Here I'm gonna discuss 3 example cases, and 2 are going to focus specifically on the complementarity between cosmic and terrestrial detections, and the third will be a case that primarily relies on cosmic detections. And I'm also going to, span not the entire mass range, but from something like 10 to the minus 12 EV to, a few tens of GeV. Okay, so let's dive in here. So one of the things I want to stress here is that, I think we have a really exciting thing here where we can measure things in so many different ways. And actually, I just want to go back here really clearly and just see that, at these masses that I particularly picked, you can see that there are cosmic probes and also other ways to find things. And so, that's really exciting. Okay, so in example 1, I'm going to talk about a light thermal dark matter candidate that has dark matter and nucleon interactions. So many of you, if you haven't seen this version of the plot, you've certainly seen the right hand of this plot many, many times. And what I want to show you here is that, you can expand this and then cosmic probes contribute for particle dark matter over a much wider range of masses. So they can provide a lower limit on the dark matter mass. This is for particle dark matter. from small scale structure. And they also provide an upper limit on the cross section between dark matter nucleon interactions. You can get different kinds of limits from different kinds of small scale structure measurements and also from the cosmic microwave background. So there's a current interesting excess in low threshold detectors between a few hundred EV. Probably it's something else going on that's not dark matter, but let's just hypothesize for the sake of argument that that was a tiny hint of dark matter. How would we, if it were dark matter, what would we see next and how would we confirm it? So SuperSyd EMS is going to turn on some lower threshold detectors in a couple of years. And let's imagine that they continue to see some events, at this mass of roughly 50 MeV. Okay, so that will also have potential cosmological signals. So here's an example of one of the cosmological signals. So one of the most exciting things that's happened in astrophysics, in my view, in the last 20 years or so, is that we've detected a whole bunch of new satellite galaxies around the Milky Way. So we used to know of like 12, now we know of about 60. These are dwarf galaxies that have their own dark matter halos orbiting the Milky Way. And we currently know of about 60 of them. But we haven't probed the whole sky. And we also, our searches are not yet sensitive to get the whole Milky Way halo. And so we predict based on this that you would have of order 200 Milky Way satellites over the full sky. And we also predict that Rubin LSST survey would expect like 100 more of these in half the sky if dark matter is consistent with cold dark matter on these scales. And also if we don't hit the limit of the mass at which galaxies no longer form. Okay, so that's what we would naively expect. So let's just imagine that the first analysis of Rubin, their first search for these new systems doesn't find very many. Let's imagine that instead of finding, 100 or 50, that they only detect 5. Well, that would be an extremely interesting result. So why would that be an interesting result? Well, it turns out there are lots of particle physics models that can suppress small scale structure. So we have measured the large scale structure really, really well from the kind of program that you've heard about from Kyle. So this is just showing the linear matter power spectrum as a function of wavelength. You can also think of this as the temperature of the universe, or equivalently of the relevant halo mass that is forming at that temperature or at that wavelength. Okay, and so there are a bunch of things we're really well measured here on large scales. There are a bunch of different kinds of things that can happen on small scales. Okay. So these are a few examples. I'm going to focus at the moment on this blue line, which is a model in which dark matter and baryons interact. Okay, and you would get this suppression in small scale structure, and you actually would also get these dark acoustic oscillations, which are what you're seeing in these wiggles. So if that were the case, right, this collisional, can't use this thing. Okay. This collisional damping due to dark matter baryon scattering at early times suppresses the power on small scales. And it does it in a way that's very analogous. Those of you who are familiar with how warm dark matter works, it happens almost exactly the same. So you can kind of build an analogy between those two models. And the basic idea is that the mass of the smallest halo that can form, it corresponds to the size of the horizon when the momentum transfer equals the Hubble rate. And so we have current constraints from these kinds of models from both dwarf galaxies. What I was just telling you about, the existence of these 60 galaxies tells you that these interactions cannot be very strong. But we also have independent constraints from the Lyman alpha forest. So this is another way to look at small scale structure and basically using the measurements of the Lyman alpha forest from background quasars. They are currently seeing this small scale structure. And so this provides this kind of limit. Okay, now let's imagine, again, that this first analysis of Rubin data only detects these 5 new satellites. So that is either an indication of suppressed small scale power, or it's an indication that we've gotten to the limit where, let's say a 5 × 10⁷ solar mass halo is not able to ever form galaxies. And so we couldn't just from this data set tell which, but either of those would be an interesting possible result. So how do we tell the difference? Well, as I mentioned, there are multiple probes of small scale structure, and these are just 3 of them, and some of the facilities which can speak to them. So the Lyman alpha forest, I mentioned already, the basic idea is you have a background quasar and there's some gas in the way, and that gas leads to some features in the spectrum. And right now, the best constraints from Lyman alpha forest power spectrum come actually from 2 things. They've come from a very large number of low resolution spectra from Sloan or BOSS, and they also come from a small number, about 15, very high resolution spectra, which include measurements from Keck and VLT. And so the numbers of those quasars that we will get will expand dramatically with DESI. And with future spectroscopic instruments like the ELTs, we will be able to make higher resolution measurements of those quasars, and that should also improve this. Now, strong gravitational lensing is another very exciting probe because it actually allows you to go beyond the scale of galaxy formation. You can detect dark subhalos, whether or not they have a galaxy in them. So it has potential to go further down the power spectrum than just dwarf satellites do. This image is an example of a detection of a roughly 10⁹ solar mass halo from ALMA. And this can be done either in the optical or in submillimeter. And so we expect to detect a large number of new strong gravitational lenses with Rubin. And probably many of you in this room saw the spectacular gravitational lens that we saw for the first time this week from JWST. I mean, you can just look at that thing and see dark matter. It's incredible. So, you know, the combination of these wide field instruments, which allow you to detect these things with very high resolution instruments like JWST and ALMA, will really be able to push the forefront of this science. Another very exciting probe that I would say is really still in the developing stage, but has a lot of potential, is the idea of stellar streams. So those dwarf galaxies, as they accrete onto the Milky Way, they get disrupted and they leave a trail behind them. That is actually relevant for both dwarf galaxies and globular clusters. And so the process of hierarchical structure formation should create a lot of these streams in the halo. We are just starting to detect those, and there's now, I think, at least 12 distinct streams. It's actually sometimes you get different pieces of the same stream that have been mapped out. We expect to detect more and longer, more extended ones with Rubin. We expect to actually be able to take spectra of the stars with DESI. And what's exciting about those streams is not just the prediction that we get for the streams themselves, but the fact that dark halos, maybe even as small as 10⁵ solar masses, can punch through those streams, and then we should see gaps in them. And so that is actually, I would say right now, has the potential to probe for the smallest scales possible. There's still a lot of theoretical development, modeling development that's needed, and much more data. But this is a place where the stage 5 spectrograph that you heard about from Kyle could also be really effective. Okay, so now let's imagine that all of these things actually find less substructure than CDM predicts below the threshold of galaxy formation, really indicating that it's not just it's not just that these things can't form stars, but really that those subhalos do not appear to be there. So that would be really exciting, but it might not convince you. There's another effect, another astrophysical effect of this same potential dark matter model, which is that they can actually, the dark matter at this energy scale can heat very dense objects, and that that could happen both in exoplanets like hot Jupiters and also neutron stars. And those could, for example, be measured by JWST. So the basic idea is that these, if there were some dark matter heating, both of these could be hotter than you would expect otherwise. And that, this is an example from a paper by Rebecca Lean and collaborators, which shows that these would be hotter as a function of distance from the center of the galaxy, because there's more dark matter in the center than there is in the outskirts. So these ones, exoplanets over here would end up being hotter. Okay, this might also, this particular model of about 50 MeV might also show up in the CMB. And in this case, the idea is that an effective is impacted by dark matter baryon interactions. And CMB measurements here showing up the current measurements and measurements from the future Simons Observatory and then CMBS4 can actually put a lower limit on the dark matter mass due to its impact on an effective. Okay, so let's say we now have a lower limit of say 10 MeV, and we continue to see, like by this point, several low threshold experiments have continued to see events at this energy scale. So we've got lots of different lines of evidence. We've got a tentative hint of these really interesting experiments. You could really then design a direct detection experiment, which is really designed not to get things at the threshold, but to really measure the peak in the velocity distribution, not just the tails. And that would give you a much more solid understanding, and you can actually do that with multiple techniques. One more thing is that if this particle were there are other experiments, for example, accelerator experiments, that can actually give you more clues to the interactions of such a particle. And to give one example, LDMX could disentangle the mass scale from the coupling of a new dark matter standard model interaction. Okay, so I think that's a really exciting first example. Next example is, imagine that you have an axion-like particle that has interactions between axions and photons. Okay, so here's another plot from the CF3 white paper, which sort of expands this range that you might have seen of how to probe wave-like dark matter all the way to the full range that is potentially probable by cosmic probes. And one thing you can see again is that cosmic probes actually can rule out the smallest masses here because of their impact on small scale structure. And there's a bunch of probes here, including CMB and including probes of extreme environments that can put a limit on the axion photon coupling. Okay, so let's imagine that advanced LIGO, which I believe just turned on again, observes a continuous wave signal that has a frequency of somewhere between 300 hertz and 15 kilohertz. So that could potentially indicate, this is detectable now, and it could potentially indicate that there is an axion which has mass of somewhere between 10 to the 13 to 10 to the 11, 10 to the minus 13 to 10 to the minus 11 EV. And the basic idea here is that black holes, if they're spinning really rapidly, can super radiate, and you get a boson cloud around those spinning black holes. And this would actually give you a signal in advanced LIGO. So this search has actually been, the first search was just done of this, and there's still potential to detect this. So this would be very exciting because it would give you a very clear idea. So first of all, this would not have to be dark matter. It would just be an indication of some sort of axion that is doing something, but it would give you a very clear indication of where to look in future cavity experiments, NMR experiments, and lumped element experiments. Okay, so this is kind of where that would be indicating. Somewhat counterintuitively, this kind of detection actually gives you an upper limit on the axion photon coupling, and so it would be somewhere in this range if it were a dark matter candidate. So then here's a nice summary of some of the parameter space that is accessible from the next generation of experiments from the draft CF2 white paper. And the basic idea here is that you would do a targeted search in NMR or cavity experiments at roughly this mass range. So let's say we saw something. Really exciting is that really then enables a map of the dark matter density and velocity in the dark matter halo. So just summarizing this candidate, since I know I have to move on, basic idea is you would see some signal in the gravitational wave experiment. let's say you do a targeted NMR search and you actually make a detection, you can then expand a range of experiments that can target this mass range, including NMR, SRF cavity, and lumped element experiments. And if you detect this in all of these, you heard about this a little bit from Tracy, I think it's a very exciting future because you actually can map out the density and velocity of dark matter halos in the Milky Way's halo at the solar circle as we're, transiting. And it gives you, sometimes this is called dark matter astrophysics. You're actually now measuring, the dark matter directly and learning in detail a lot more about the formation history of the Milky Way. One of the exciting things is that we are simultaneously making astrophysical measurements using stars, and we can then connect those directly, the stellar density and velocity with the dark matter density and velocity. So I think that's a very exciting possible future. Okay, last example. Here's an example where we have dark matter that has self-interactions and also has suppressed small-scale power. So basic idea is that self-interacting dark matter can suppress the density profile in a wide range of halo masses. And it can do that in a velocity-independent way or a velocity-dependent way, which tells you something about, in either case, about how it's coupling. And we can do that over a range of mass scales. So we can do it on cluster scales. We can do that with really our next level of precision in weak lensing experiments from Rubin. We can combine that with X-ray measurements and also with strong lensing from, say, JWST. We can also do this with dwarf galaxy profiles. And for example, using the stage 4 spectrograph would be excellent for this, along with the ELTs. And so we can sort of, let's imagine that we independently measure cores on both of these mass scales and are really convinced that it is, not a feature just of the baryonic physics. Let's imagine now that we have a similar observation to the one I told you before. It's now going to have a very different physical motivation. Let's imagine again that LSST only detects 5 satellites, which is fewer than we expected. And let's imagine in this case that actually strong lensing and streams see the impact of dark substructures at, say, 5 × 10⁸, but that when you go further in these experiments that probe small scale structure and can do it beyond the scale of galaxy formation, that they very clearly see missing power. They really are not seeing as much small scale power as you would have expected. So this is an example that would look quite a bit like warm dark matter, where you have this clear suppression at a given scale. So this could be a version where you have 10 keV dark matter that also has self-interactions. And here's an example plot from the CF3 draft report about how you could make such a measurement with Milky Way satellites from LSST, where you also measure their profiles. Now, that suppression of small scale power could also be consistent with 10 GeV dark matter that is coupled to a light mediator and dark radiation, which would actually suppress small scale power in a similar way to that 10 keV dark matter. And one thing that's really nice about these self-interacting dark matter models, if you can measure the profiles at different mass scales, this can actually pin down the dark matter mass really well. So in this latter case, where it's actually a 10 GeV dark matter, there will also be a signal in N effective as measured by the CMB that would give us an additional clue to what's going on here. Okay, so I just want to highlight in the stories that I told you, first thing I want to highlight is what a wide range of astronomical observatories will be relevant to the next generation of dark matter searches. What I have here is actually just a very partial list. Let me say that I think most of these observatories are motivated either by a very broad astrophysics program or by the kind of dark energy and inflation arguments that you heard about from Kyle. but many of them are directly relevant to this dark matter astrophysics program. So again, I just gave 3 examples. Those are 3 examples of many, many possibilities. And just to highlight exactly the role that cosmic probes were playing in these 3 examples. In the first example I gave you, where we had signals of suppressed small scale structure, extra heating in dense objects, and then detection in low threshold direct detection experiments, the cosmic probes initially helped distinguish dark matter from background events and kind of motivate us to better go look for them. They then informed the mass and interaction strength, and then they really motivated this expanded direct detection and accelerator experiment. In the case of this axion-like particle, where we had a signal of black hole superradiance and detection in terrestrial experiments, the cosmic probes really provided the target range for that search, which then actually enabled not only a detection, but actually mapping of the dark matter halo and connection to the formation history of the galaxy. And then in the third example, this is an example where we had these self-interacting dark matter combined with small scale power. The cosmic probes really are the primary window, and we may not have had that, that whole set of exciting signals that you heard about from Tracy. But I think, what's exciting here is the range of possibilities and the fact that this combination of experiments and cosmic probes, which can probe almost the entire range of the possible dark matter mass, really give us not just one discovery window, but a very, very vast range. And there's really quite a bit of complementarity across the cosmic frontier, but also across other frontiers, a real need for detailed modeling and a robust theory program, and a really wide range of experiments and astronomical observations will be relevant in each of these cases. So I personally am really excited for this decade.
All right, thank you very much, Risa. Let's see, maybe check from the remote audience first. Nothing? Not yet. Okay, any questions from the people in this room? Oh, great.
So this is so inspiring, Risa, by the way, you have to be congratulated on your own contributions to many of these things, which have been so spectacular. You didn't even tell about all the things you've done. But what about the problem of baryonic interactions that make cores? When we see a core, we don't know that it wasn't made just because baryons were having supernovae or whatever, and even if there aren't any interactions between baryons and dark matter, so you're implying that that'll eventually be controlled well enough that we can.
I believe it's possible to control it well enough when we really bring the full suite of observations and modeling that we have at our disposal. Yes, I do. I mean, the first thing is that most of the things I told you about actually don't depend on that, and it's one of the reasons that I really like these dwarf galaxy searches, which are mostly depending on counts. Literally, it's the existence of these things without worrying about their profiles. But that's just a personal taste. I mean, I think in this self-interacting case that I gave you, it absolutely does depend on really understanding the profiles and understanding the baryonic physics. I think we have a few things that will help us in that quest. The first is multi-wavelength observations. So the fact that we have weak lensing and X-ray, which actually behave somewhat differently and can help break degeneracies, that is very convenient. A second thing is the fact that we are looking at, we have the possibility to look at very different mass scales where the impact of baryons is very different. So that's very helpful. And the third thing is that, I think the modeling is getting quite a bit better. I think there's a whole program that people have been pursuing, but I think will mature significantly over the next decade, where we really can start to say, not just like, I have a model, it has some baryonic feedback. I have another model, it has some baryonic feedback, but really start to use the observations to bound what's possible. And I think there are distinct enough signatures in these things that it is possible to do that.
Thank you.
Great. Any other questions for Risa? Everything was fantastically clear, compelling. We're all ready to sign up.
Yeah, so which again, going back to the question that I was asked at the end of mine about, so what would you do if you don't see anything in the broad program that I discussed? I think Risa has answered that, but I don't think we should wait a decade, right? I mean, like we haven't seen, you know, we are currently at a point where we have not seen confirmed, where we have a broad program. And I mean, like I said, I'm very excited about the breadth and versatility of the program searching for dark matter signals with the standard model going forward over the next decade. I think it's really opening qualitatively new areas of parameter space, and we'll probe some new things. But at the same time, we have these amazing cosmic probes that can tell us really important things about the properties of dark matter in the environment where we can actually see dark matter. So, you know, so my answer is that if we still haven't seen anything in all these searches by next NOMAS, then this will take on increased urgency of learning everything that we can from this. But we should be starting now, or previously, of course. I know there is, of course, a major effort to do it.
And I think we have started, and I think, I mean, one of the things that I'm encouraged by is how quickly this program has actually matured over the last 5 years or so. I mean, I think, you know, in the last SNOMAS, people weren't talking about, you know, exactly what kinds of the breadth of interactions that not just the masses, not just where the dark matter is, but really what are the interactions and how does that impact all of these astrophysical probes? And I think it's matured both because the observations have gotten a lot better and are, you know, a lot more powerful, but also because of the theory development and the growing collaboration between particle theorists and structure formation theorists that I think has really pulled this together. And I think a lot more is needed there.
Completely agree, for what it's worth.
Yeah, one more question.
Over here.
Can we get very creative and think of a terrestrial experiment for self-interacting dark matter?
So there are some versions of the case I told you, which would have terrestrial implications, and there are some that would be detectable at accelerators, and there are some where maybe the dark matter would not be detectable at an accelerator, but the light mediator would be detectable. So the specific version I gave you was a little bit hard to tell that story, but there are many other versions that are easier to tell that story. And so, yeah, I think we should be an optimist about this. Tracy, yeah, you might have better.
I just wanted to make like a slight plug for the ultra heavy dark matter stuff in CF1, which is not self-interacting dark matter, but is an example set of scenarios where people think about terrestrial experiments to actually probe the purely gravitational interactions of very heavy dark matter particles. So that's something that could potentially be done as well. But no, I mean, I think Risa's answer was perfect for the self-interaction question.
And then I guess I can make a comment on the Axion dark matter stories. It would be very, very helpful for those of us working on Axion searches for somebody to tell us, to narrow down the search window, tell us exactly where to look, because these experiments are usually they're resonant experiments, which means we can only check one mass hypothesis at a time. And given that there's only like 10 to the 7 seconds per year, we can budget at most 10 minutes for each mass that we're probing, and then we have to tune the radio and like check the next mass. So if Risa or others could tell us exactly where to look, we could just sit there on that line for hours if we want and see the signal very quickly. So that would certainly be very, very helpful.
That would be great.
Okay, any more questions? Okay, so if not, I guess we'll close this session and head out and get some coffee. So thanks again to Risa, to Kyle, and to Tracy for some really excellent talks.